Hey folks, we have another day of working through the practice test. Let's go ahead and get started. Um, so let's look at this question. Give an algebraic proof for this identity here. So let's just work out what this left-hand side is saying and work out what the right-hand side is saying. So the left-hand side is n squared plus 2 times n factorial over 2 factorial times n minus 2 factorial, which is the same thing as n squared plus 2 times the n factorial and the n minus 2 factorial is just going to leave me with n times n minus 1 on top. And then there's going to be a 2 factorial on the bottom, but that's just a 2. And these 2's are going to cancel. And so this is just n squared plus, and then n times n minus 1 is n squared minus n, or 2n squared minus n. All right. So how is that going to relate to the right-hand side? Well, this is the same thing as how do we want to write this out? Two n times n minus 1/2, which is the same thing as 2n times, I'm going to simplify this fraction here by getting a common denominator. This is 2n over 2 minus 1/2, which is the same thing as 2n times 2n minus 1 over 2. But this is the same thing as 2n factorial over 2 factorial times 2n minus 2 factorial. Let me explain this step here. The 2n factorial, this term here over this term here, is just going to leave me with 2n and 2n minus 1 on the top. And the 2 on the bottom is your 2 factorial. This is 2 times 1, but that is the same thing as 2. But this is 2n choose 2, which is the right-hand side. And so these two sides are identical to each other. Let's move on. In Java, a legal variable name must meet these requirements. The first character is an uppercase letter, a lowercase letter, a $sign, or an underscore. So there are 26 uppercase letters, 26 lowercase letters, and then there are 2 special cases. And so there are 54 letters that we could start with. Subsequent letters could be a uppercase letter, a lowercase letter. So that's 26 of those, 26 of those. A digit, a $sign, or an underscore. And so that's got to be 52, 62, 63, 64. And it cannot be one of the reserved words, but for 3-letter names, there are only these 3 letters, okay? And so the question is, how many 3-letter, how many legal variable names have exactly 3 characters? That spread on over to the next slide when I was doing this, but there are got to be 54 characters for the first position, 64 characters for the second position, 64 characters for the third position. The order matters, so we do not want to divide by anything. So we don't divide. But then we want to subtract the 4 special cases. And so what we're going to get is 54 times 64 squared minus 4. Okay? All right, let's move on. Number 11, 7 people are running for 4 seats in a town council. It doesn't matter now what order these 7 people are elected. If whoever comes first, second, third, or fourth, those top 4 people take the 4 seats, even if they came in first, second, third, fourth in a different order. So the order doesn't matter. So this is a combination problem. And so we just need to fill 4 seats out using 7 people. So that's 7 choose 4, which turns out to be 35. All right. But here, 3 from District 1 and 4 from District 2 are running for 4 seats from Town Council. The bylaws specify there must be at least 1 representative from each district. And how many ways can the 4 seats be filled? Well, there's only one way. One way of filling 4 seats that violates this rule. Since there are 4 seats and only 3 of them from District 1, I can't fill all 4 seats with District 1 candidates because the 4th seat would have to go to a District 2 candidate. I could fill all 4 seats with District 2 candidates, and that would violate the bylaws. There wouldn't be anybody from District 1, but I would have to use up every single District 2 candidate to do that, and so that only happens in one way. So there's only one way of filling 4 seats that violates the bylaws. All 4 District 2 candidates win. And so we just deduct that one case. And so there are 34 ways of filling out the 4 seats if we eliminate that one violating case. Okay? This is a problem, I think, that's much easier to do by subtraction instead of by addition. Okay, let's move on. A florist has a large set of red, pink, and white roses. Customers can order a bouquet of a dozen roses in any assortment that they want, or write a binomial coefficient that gives the number of possible bouquets that can be ordered. And so a specification will include 12 ones, in other words, 12 instructions to pick a flower, and 2 zeros to move to the next color. Okay, and so my program to pick this bouquet will have 14 spaces with which 12 will be ones. 14 choose 12. This is consistent with the formula n plus r minus 1 choose n, where n is 12 and r is 3. There are 3 bins and 12 roses to be picked from. All right. So that's that problem. Let's move on. Small hardware store has in stock 3 C-size batteries, 4 D-size batteries, 6 AA size batteries, but they're in packs of 2. write a generating function that can be used to find the number of ways of purchasing batteries. So for the C-size batteries, we can go anywhere from 0 to 3. For the D-size batteries, we can go anywhere up through 4. And for the AA batteries, we have to go by even numbers, but up to 6. And that would be our generating function. Okay. A bakery sells muffins individually and in boxes of 3 and 5. Find the number of ways of purchasing 10 muffins. Okay. And this problem wants an exact answer. This is a small enough problem that we could actually just sort of count this out. We could have, so for the number of boxes of 5, we could have 0 or 1 or 2. Well, if we have 2 boxes of 5, that is 10 muffins, and so we're done. One way. If we have 1 box of 5, we have 5 more to pick. So if we look at boxes of 3, we could have 0 or 1 box of 3. We couldn't have 2 boxes of 3 because that would take us up to 11. And so then the rest would have to be made up with individual muffins. This would be 5 plus 3 is 8, and then plus 2 individual muffins. And 1 and 0 would be still 5, so we would need 5 individual muffins. If I have no boxes of 5, that's 10 more to pick. And so for my boxes of 3, I could go all the way up to 3 boxes of 3. Plus, I would still need 1 individual muffin left over. 2 boxes of 3 would only be 6, so I would still need 4 individual muffins. 1 box of 3 would require 7 individual muffins. And no boxes of 5 and no boxes of 3 mean I'm buying all 10 muffins individually. The question is, how many ways of doing that? Well, we've written them all out. It's 1 way here, 2 ways here, so that's 3, 4, 5, 6, 7. 7 ways. Okay. If we didn't want to do this by just brute force counting, the alternate solution would be to do this using a generating function. The boxes of 5 could be 1 plus x squared. The boxes of 3 could be 1 plus x squared, let's start over. The boxes of 5 could be 1 plus x to the 5th plus x to the 10th. Boxes of 3 could be x cubed, x to the 6th, x to the 9th. And then the individuals could be all the way up through x to the 10th. And really, we're looking at the ways of combining these 2 terms that still leave me with individual muffins that don't go over 10. And so the ways of combining those would be these 2, these 2, these 2, 5 and 6 goes over, 5 and 6 would be 11, or an individual muffin in any of these terms. Or this one, this one, this one, or this one. And that's 1, 2, 3, 4, 5, 6, 7 possibilities that way. All right. Let's keep going. We've got a few more problems to work through. Compute the value of the generalized binomial coefficient, -6, choose 4. So that's the same thing as having a 4 factorial on the bottom. And on the top, we start with -6, and we go down, but the same number of terms. So the next term will be -7, the next term will be -8, and the next term will be -9. So that there are matching numbers of terms here. All right, so negative times negative times negative times negative is all positive. I have 4 negatives, so I don't have to worry about that. The 3, the 2, and the 1 cancels with the 6. And the 4 partially cancels with the 8 and leaves me with the 2. 7 times 9 is 63. 63 times 2 is 126. Okay. All right, a deck of playing cards contains 52 cards, with each card having one of 13 ranks and one of 4 suits. Full house consists of 3 cards of one rank, along with 2 cards of a different rank. Find the number of possible full houses. So my specification might be is to choose one rank. Choose 3 cards of that rank. Then choose a different rank. And then choose 2 cards of that rank. All right. So there are 13 ways of choosing the first rank. There are 13 ranks available. And out of the 4 suits, we need 3 cards out of that suit. Then there are 12 ways of choosing the next rank. And then there are 4 choose 2 ways of choosing 2 cards of that rank. And so we get 13 times 4 choose 3 times 12 times 4 choose 2. Okay. All right. Let's keep going. Number 17. Despite the band's names, there are currently 6 members of Maroon 5. We're going to seat them at a round table. If the orientation is significant. So some of these seats may be a little bit more comfortable than others, or have less light in your eye, or something like that. And so maybe the most important member of the band goes here, and then so on and so forth. Well, then what happens is that there are 6 members that can fill the first space, and then 5 members that can fill the second space, and so on and so forth. And that gives me 6 factorial ways of doing this. Okay. If the orientation of the table doesn't matter, then this seating arrangement, A, B, C, D, E, F, is the same as this seating arrangement. That is because the orientation of the table doesn't matter. And so out of these 6 orientations, they cluster in groups of 6. 6 of them are different rotations of the same thing. And so we would get 6 factorial divided by 6, which turns out to be only 5 factorial. Okay. How many ways of there seating them in a round table if Adam and James won't sit next to each other? Well, there are 2 cases that we want to exclude. Either that Adam and James are sitting with James on the left and James on Adam's left and Adam on James's right, And then there are 4 factorial ways of putting everybody else down. Or James can be on Adam's right and Adam can be on James's left. And then there are 4 factorial ways of doing this. And so 5 factorial, because we're told that the orientation doesn't matter, so we're starting with part B, minus 2 times 4 factorial. That will get us through part C. All right, number 18. Use the generalized binomial theorem to determine the coefficient of x to the 4th in this power series. So this is the same thing as 1 over 1 minus 2x raised to the positive 3. By the generalized binomial theorem, this is a sum as n goes from 0 to infinity of negative 3 choose n times negative 2x raised to the n power. Okay. So the question is to what is the coefficient of x to the 4th? So what happens when n is equal to 4? Well, that's negative 3 choose 4 over negative 2x to the 4th. This will have 4 factorial on the bottom. This will have negative 3, negative 4, negative 5, negative 6 on the top. Those are all negatives. And then negative 2x to the 4th. So negative 2 to the 4th is positive 16. The negative signs here cancel because there are an even number of them. The 4 and the 3 cancel. And so we get 5 times 6 over 2 times 1 times 16. So the 30 over 2 is 15. 15 times 16 is 240. All right. Sounds good. Good luck getting ready for this test. Good luck finishing the homework that's due tonight. I'd say have a good weekend. Have a productive weekend up through the test, and then find some time to enjoy yourself Saturday evening and Sunday. All right? Take care. I'll see you guys around.